All right. Welcome. Good morning. Good evening. I know last day I promised I'm going to stick to the textbook, blah, blah, blah. But then I don't know, I just like the flow of my notes a little bit better. So I posted the chapter 2 notes. I used to call it chapter 1 part 2, but honestly, it's the same breakup as the new chapter 2. So I just renamed it chapter 2 and posted it there. And they should look something like this. Okay. The reason I wanted to stick with these ones is because it does include some R code, which I do want to introduce you to. And so that's why I made a decision, and I'm sticking with my notes for just a little bit longer. Okay, so we're going to start by looking at numerical data. Typically, I would do a little bit of review, but in terms of review from last day, I had to look back and remind myself, but what we talked about last day were things like, how do we pick a random sample, right? We need a random sample for it to be representative of the population. All right. I'll write it down. Turns out we will have a little bit of review anyways, but not much, mostly because it doesn't really play a huge role today. So what we're starting today is kind of fresh. So I don't want to bog you down too much, right? But we need our sample to be representative. Representative of the population in order for our results or analyses, results/analyses to be reliable, right? If we're drawing conclusions using something that doesn't really represent the population that we're trying to talk about, you can see how your conclusions would be unreliable, right? And so we need our sample to be representative of the population. How do we do that? The best way to do that is to make sure that we've collected a random sample. We do that by ensuring our sample was randomly selected. And we talked about a couple of other methods that we could use, right? We could go a little bit fancier and talk about maybe we use a stratified random sample, or maybe we use a cluster sample, and we talked about those differences, even a multi-stage sample. But typically we would just use a simple random sample where we just take a random sample from the population, and that ensures that it's representative of the population. Okay. So that's kind of the main takeaway from last day. And we talked about other stuff too. The main thing about experiments that we ended on was an experiment is the only way that we can establish a causal relationship. So being able to say that A causes a change in B, right, where A is something and B is another variable, right? Right, the only way to be able to say that is to conduct an experiment. But not only that, conduct an experiment where you control every factor that might affect the response variable. Okay, and so the only way to establish a causal relationship right? Being able to say something like A causes a change in B, right? That would be a causal relationship, right? So the only way to establish that is by doing an experiment and controlling all factors that might affect B in this case, right? From this example here, right? If we're looking at the change in B, then B is the response variable. In fact, maybe I'll clarify here that might affect the response variable. And then I'll put in brackets, capital B, right? Referring to here, right? This kind of causal, A causes a change in B. A would be the explanatory variable, and B would be the response variable in that case, right? If we're concerned with changes in B, then that makes it our response variable. Hey, look at that. It's turning into quite a review of last day. Oh, well. A reluctant review. All right, but that's where I'll end that, okay? Today we're gonna start talking about, okay, so we've collected data, we're able to identify what types of variables we've collected, right? And so now the next step is, how do we summarize this data? How do we look at this data to see what's going on, right? And so where we start is just through data summaries. We're going to start by looking at numerical data, and that'll be today. And then I think I'm so thrown off by meeting tomorrow again. I'm used to like every other day situations, but anyways, I'll get used to it, I think. So then tomorrow we'll either finish numerical data because it's quite a large section, or we'll start talking about categorical data. How do we talk about and summarize categorical data, right? So we'll kind of keep them separate. So again, it's so important that we're able to identify if we have a numerical variable or if we have a categorical variable, because what you'll see is how we summarize them and how we visualize these will depend on what type of variable we have. Okay? So I'm using these chapter notes. Hey, maybe like that. All of it. Okay. So I like to get us in the groove here. But first, I'm going to call this chapter 2 since they broke it up. Okay. Great minds think alike. I'm very pleased that they did the same breakup that I did. Anyways, oh well. So like I said, right, once we have a data set, so hey, sometimes I see these emojis and it's so funny. So once we've collected our data, right, we need to get a feel for what's happening in here. Okay, and so the main thing that we do is data visualization. So we'll start there. And the point of data visualization is just to quickly communicate what's happening in the data. Okay, and so the main thing that I want you to remember for data visualization is that it has to provide a clear and concise summary of your data. Not all your data, but maybe of your data or variable, right? Often we'll just focus on one or possibly two variables. How are they related? And then we kind of move through our data set, looking at pairs, and we'll have tools for working through that. But the key thing is that when you've made a visualization, no matter what it is, right? The main thing that I want you to remember is that someone who doesn't know what you're talking about, right? So who has no clue about the data, should be able to look at your graph, and they should be able to understand what's happening. So it should be really simple, right? And you shouldn't have to explain a lot of things. And that's where people go wrong a lot of the time is they want to make these complicated graphs. But that's not the point, right? The point is to keep it simple. And so when you hand your report over to your boss can look at it and say, oh, I see, and then put it to the side, right? And so that's how quick this communication should be, right? And you can make use of things like a legend, right? But you don't want to have a huge legend where there's a lot of explaining to do. You want to keep it as simple as possible, okay? So here, a successful data visualization should require minimal explanation, okay? So that's just something that I want you to kind of internalize and hold with you as you're creating graphs later, right? Just take a step back and think, someone who doesn't know what's going on here, are they just going to be able to look at it and understand? So what I have here is kind of a fun example. So of course, Facebook, Twitter, Google, whatever, they're at the forefront. They've got cool people working on cool data visualizations, right? And so something like this, I mean, it's very nice to look at, right? So Facebook connections, this is kind of an old graph, but right, it really highlights how simple a visualization should be. So just looking at this, we understand what's going on, right? Each little line is a Facebook connection, and they're going across the pond, right? Of course, it's only part of the world, but right. And we see that as things get brighter, right, there are more Facebook connections and so on, right? So just having that label, Facebook connections, I think so. So I grabbed this one when I started teaching, and I use it every time I teach this course because I like it so much. I think it's so beautiful. So I'm assuming it's from real data, but it's probably outdated, and they probably have the fresh one released. Yeah. So yeah, I think it's just beautiful, and it just highlights how simple things should be, right? Whereas here, I've got this bad visualization, right? And I love these. Exciting, beautiful, technical. We have no clue what any of this means, right? And so there are all these little bubbles. I guess the image quality is not that good, but they all have little measurements like 0.45 and 0.65. But when I look at this, and then I don't know what this is, Center for Mathematical something. When I look at this, I have questions, right? I have questions like, does the distance from this clearly main blob, does that matter, right? So this yellow one, this yellow circle being so close to here, does that mean something, right? Or is it the same as this one? They look the same, but they're different distances apart. Okay, there seem to be two layers. What's the size of the circle? I don't know, right? And so I have no doubt that someone spent a lot of time creating this, and I'm confident that it is a beautiful summary of very complicated data, right? And that's fine. But it's not very useful, right? We don't look at this and say, oh, I understand. We have no clue what this is, right? And so even though it looks cool, right, and it looks technical, and that's, you know, fun, but this is something that we want to avoid, right? We want clear, concise visualizations. Okay. So I think these two examples are just so fun, just the contrast. But anyways, good. I guess I should probably look up, maybe Twitter has some fun visualizations that I could steal. They like to do word clouds. Of course, Twitter is in the business of words. And so maybe they'll do word clouds, cluster analysis, that kind of thing. But I haven't looked into it recently because I've got two winners here, right? All right. So for us, we're going to start slow, right? Because we might not have any experience in visualizing data, right? And so for us, when we visualize numerical variables, we're going to use what's called a histogram. So I'm going to pull this in here. Okay. And I know these look boring compared to the Facebook one. But this is where we're starting, right? And we can make these fancier. You can do weird things like make them colorful or something like that. But there's not a whole ton that we can do to make it beautiful, but they are easy to look at, right? And so even if you don't really know what's going on here, right? I think when you look at it, hey, good morning. I think when you look at it, right, we kind of get an idea of, all right, what does this data set look like, right? So I've got histogram 1 and histogram 2. We can see right away that they have slightly different shapes, right? And so we visualize the data to look at the distribution of it. Okay, and we're going to use that term distribution a lot in this course, right? So we need to consider the distribution of the data, but really that's just talking about the shape of the data. Okay. So here, right, when you see distribution of data, distribution of data is really just the shape of the data. Right? So just generally describing what does this, I almost said distribution, what does this shape look like, right? What does this variable look like? Okay. And so I think what you'll find is that let's pretend that you're on the phone, and it's a landline because it's like a banana one. So you're on the phone and you're talking to your friend and you have to communicate, what does histogram 1 look like? Okay. And so, all right, first thing you would touch on is, sorry, I'm still on the phone. First thing you would touch on is the shape, right? And so we need to have shapes available to us that we can talk about, right? But then we might also want to talk about things, now I have to write, like the center, right? I never hold the phone like this with my left hand. So here, right, we want to talk about the center because that tells us where most of the data is located, right? And then another thing that might help us describe this thing fully would be the spread, right? And so the spread being from 10 to 40 tells us something as well. Now, at first, when we just look at these, right, I just want you to eyeball it, right? There's no math involved because we're going to develop those math skills in a little bit, okay? So when you're looking at a histogram, right, we're going to talk about the shape, we're going to talk about the center, and we're going to talk about the spread. But the shape, the center and the spread are just quick eyeballing. So when I used to work at the market research firm, people would ask me, "Oh, how did you find that? How did you know that?" And usually my answer was, "Well, I eyeballed it." So they started joking that all I do is eyeball stuff, but it's true, right? We need to develop our skills for eyeballing and just kind of being able to look at something and say, oh, that's what's going on here, right? So that's going to take practice. But yeah, they thought I was joking when I said I was eyeballing stuff, but it's what we do, right? We're eyeballing and we're just kind of getting quick ideas of what's going on. I'll bring this in here. I didn't even realize the word was cut off. Common. It's on the next page. Oh well. So first we need to talk about shapes. Now, just like if I draw something like this, oh, well, that is a weird shape. I want it to complete the shape for me. Haha. Right. Just like if I draw something like that, you would probably call it a rectangle, right? If I draw something like this, you'd call it a circle. Okay. And so just like recognizing those shapes is so basic, right? We need shapes for distributions. Now, the most common shape that we have is the normal distribution. Okay. And so the normal distribution looks like this. The name normal confuses people a lot because we have the term normal, but in this case, it's a name. If we want to get fancy, we could call it a Gaussian distribution, but that doesn't really sound that cool, right? Oh, shoot. I feel like I have a little funny for it. I'll save it. Anyways, so we can call it a normal distribution or a Gaussian distribution. I try to capitalize the N to emphasize that it's a name, right? So that we're not confusing it with just, oh, this is the normal distribution, right? But also confusingly, this is the most common distribution that we see naturally in definitely biology. So a lot of biology things, measurements that we're doing are going to follow a normal distribution. Heights of people, for example, follow a normal distribution, right? Most of us are hanging around the average, it turns out, right? That's how we get to the average, right? And then we know that there are some people that are shorter and some people that are taller. And then there are very few people who are very, very short. And then there's very few people who are very, very tall, right? And so So we kind of understand this normal distribution. So things kind of start to become less and less likely as we move out into the tails, as they're called. Okay. For us right now, okay, I just want you to look at the shape of these distributions, and I only want you to classify it as normal or non-normal. Now, of course, the non-normal distributions, and we'll talk about some of those shapes, what they might look like, the most common ones, but the main classification that I want you to do is normal, non-normal. Okay. So here, right, that's what I want you to talk about in terms of the shape. Now, we have to be really kind of generous with the normal versus non-normal, right? And so what I mean by that is, if you're going to tell me that it's non-normal, you have to argue, really argue why it would be non-normal. And the reason for that is because later we're going to be doing analyses. Now, one main assumption and one main thing to be able to do those analyses is that we have a normal distribution. So if you're trying to tell me that this looks non-normal, that closes the door to a lot of things that we could do, right? And so instead, what I want you to do is I always want you to argue that you have a normal distribution, right? Oh, yeah, I have a normal distribution, right? And so you always want to push for a normal distribution. And so instead of saying it's non-normal, I would say something like, especially here, right? If I visualize this, I just kind of drape a blanket over it. Okay. Looks kind of like this. It doesn't look as beautiful as this one, right? Histogram 2. Well, they look the same now, right? But in general, right, I would say that histogram 1 looks like it follows an approximately normal distribution, right? It has pretty short tails, right? So we want to kind of explain away reasons why it would be non-normal, right? Histogram 2 just looks like a beautiful normal distribution, okay? And so definitely here the shape is normal, okay? But in both instances, I want you to argue that it's normal. Even if you have something, and I wish I had an example, even if you have something that's slightly non-normal, right? You're going to be better off arguing that it's normal and mentioning maybe there's an outlier. So we haven't talked about outliers, but we use the term in regular kind of day-to-day language, right? An outlier would be an extreme value, right? So here, always argue or try to argue that you have, that you have a normal distribution okay, or approximately normal, right? That's usually how I get away with it. I say, oh, it's approximately normal, right? It doesn't have to be perfectly normal, but it's approximately normal. Approximately normal. Oops. And mention any outliers which are extreme values. So there are going to be cases where you might have a tail, and this is kind of weird, but what I'm going to do is I'm actually going to go into my notes from another class, because here we talked about it too, and it's just a graph that I didn't have before. Okay. So what we're going to see is that maybe we'll have distributions. So here are some different shapes that we could have. Okay. And so just eyeballing, right? It's hard to argue that I have a normal distribution here, right? Because when I look at this, right, I'm kind of stumped. I would want it to keep going like this, right, for a normal distribution. Same thing here, I've got this kind of situation. So when we're stuck in this kind of a graph, right, then we have no choice. It's hard to argue that we have a normal distribution in these cases, right? Whereas here, right, I've got this beautiful normal distribution, right? And so that's easy to argue. And even more so here, right? So what we say when we have these clearly non-normal distributions, right? So here, A, B, and D are clearly non-normal distributions. Distributions. Okay. And so we need a shape for that too, right? And like I said, for now, if you just want to classify them as non-normal or normal, rather normal versus non-normal, right? That's fine. But this situation where we have a long tail on one side, but not the other, we call it skewed, okay? And counterintuitively, right, at least for me, when I look at this, and most people, when they want to or when they have to describe this shape, right, we gravitate, we'll get to bimodal in a second. Yeah, but good. So here, most people want to talk about where the lump of the data is, right? And I think that's natural for us because we want to describe where most things are happening. So what happens in statistics is we don't care about where most things are. What we're interested in is these little extreme values. Hey, how did these happen? Right? These are interesting. Here, I know what's going on here. Everyone's over here, but we want to be over here with the cool kids and analyzing those extreme values. Okay, and so for that reason, we say that this is skewed to the left, right? Which means it's skewed in this direction. And so as a way to remember is that it's always skewed in the direction of the tail, right? We're always talking about the tail as opposed to the lump, right? And so it's always skewed in the direction of the tail. So here, this is skewed right. Right? And we can say things like moderately skewed or highly skewed, right? Depending on what the shape looks like, right? And it really just boils down to how long is that tail, right? How long is that tail going to go on for? So I think I have, can't quite remember. Okay, I don't. Okay, that's okay. Non-normal distributions, oops, are always skewed in the direction of the tail. Okay. So non-normal distributions, right? And so I'll highlight that because it throws a lot of people off. Okay. Most of the time, right, we're going to have a normal distribution, and so this is not really a concern, right? But it's good to have vocabulary around non-normal distributions as well. Okay. Let's see here. Oh yeah. I keep wanting to keep going, but I actually have more to talk about here. Wow, it's catching up. Here. Okay, it's with me. So when we talk about the shape, right, you always want to argue that you have a normal distribution. Unless it's clearly non-normal, then you've got, you know, skewed to the left, skewed to the right, moderately skewed, highly skewed, that kind of thing, right? For the center, right, the center of the data here is going to be just where is the peak of the distribution, okay? And so here, this is the center, and it's just a rough approximation, right? And so if we have a normal distribution, then it's easy, right? If you have a skewed distribution, you would be talking about the location of the most data, right? And so here, we're just eyeballing here. And for the spread as well, right? Rough approximations. So the spread, maybe I should use a different color. There's an idea. The spread, we're also eyeballing. And usually what I want to talk about for the spread is just kind of an idea of reasonable values, right? And so it doesn't have to be exact at all, right? We just want to talk about magnitudes, meaning are things between 0 and 5, or are they between 100 and 500, right? What are some reasonable values, right? And so what are the reasonable values? Right, really rough approximations here. We will develop numerical values here. Well, yeah, so sometimes we call it the range. The range to me is more the distance between the two, right? The maximum minus the min, which is also useful. But for the spread, I call it the spread because then it's from this value to this value. So sometimes I'll call it the range. Sometimes I'll call it the spread. But usually it's just to get an idea of what type of spread are we dealing with here, right? And so for the center and the spread, we're about to develop numerical summaries for those, right? Namely the mean and the standard deviation, right? And so we're going to have values, we're going to have exact values for those. So that's why we're just eyeballing it for now, okay? Yeah, so I'm not calling it the range. You can call it the range and that's totally fine, yeah. But I just want from here to here. Nice. Okay. Good. So if we're talking about these histograms, right? comparing histogram 1 with histogram 2, we can talk about the shape, right? The shape of each of these, I would argue, is approximately normal, right? Histogram 2 is more normal, but we don't need to go that deep, right? So here, both of these shapes both are approximately normal. Okay. For the center, right, if I have to describe these histograms, the center for both of these, well, just kind of, so notice I'm going to make use of my imaginary normal distribution, and then typically wherever the peak is, which we're going to call the mode later, but where the peak is, that's going to be my approximate center. And remember, this is just to get an idea, right? Are we measuring things in that are tiny, 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 right? So maybe 0.0001, or are we measuring huge things, right? 2000, right? So just rough approximations. So here, roughly 25. And same thing here, if I kind of break down the scale down here, it looks like the height of my data, so where most data are located, is roughly around 25, right? So roughly 25 for both, right? So now, okay, so they have the same shape, they have the same center roughly. Okay, what about the spread, right? Histogram 1, roughly between 10 and 40, right? Those are some reasonable values that we can use. And usually I'll just talk about whatever the cutoff points are. So even if there was, let's pretend for a second that there was a block here as well, but it only went to 40, I would still just say 40, right? Because it's just rough approximations. Okay. And so here, right, for histogram 1, so for the spread, histogram 1 is about 10 to 40. Whereas histogram number 2, okay, goes from roughly -50 to 100, roughly, right? I can see that it goes beyond, but it's not terribly important, right? It just gives us an idea. Okay, -50 to 100, those are reasonable values. Okay. Why do you think that we care about reasonable values? Right? Okay. The reason we care about what would be reasonable to see is so that we can eventually try to identify what an extreme value would be. Oh, I wasn't expecting to see that, right? Because, yeah, exactly. So do we have any outliers? And a lot of our analyses are going to be about, was this observation so extreme that it probably didn't come from this group at all? It came from a different group. Okay. So from -50 to 100. So notice the only difference here is the spread, right? But the different spreads tell us that they're probably from different variables. They're looking at different things. Right? Good. I'll bring this in here. Oh, there it is. Here it is. Distributions are skewed in the direction of the tail, but I already highlighted that here, but it doesn't hurt to see it again. Okay. So the last distribution is the bimodal distribution. Now the mode is just the most frequently occurring data point. Okay, and so the mode, I'll put it in here, is the most frequently occurring, oops, looks like a G, frequently occurring data point. The peak of the histogram. Oops. Huh? So by definition, a normal distribution is a symmetric unimodal distribution, okay, because it's got that symmetry and it only has one peak. Okay. Again, skewed distributions are still unimodal. They only have one mode, okay, one peak, but then they're not symmetric anymore. Okay. So bimodal distributions, bimodal looks maybe something like this. Okay. You need to have distinct humps or distinct peaks. Okay. There could be little spikes and kind of highs and lows within these, but what I want you to do is just kind of drape a blanket over the distribution to get an idea of the shape, right? So the specific histogram might have bars with some spaces, right? So the actual histogram here might look something, wait, come on, might look something like this. Well, I should probably have the same width. Now I'm getting lazy. The bars get wider and wider as I go. Something like that. Okay, so even though there's technically a dip here, right, we ignore small dips, right? It's just the general shape that we're interested in. Okay. So this would count as one mode, and then here's another mode, making two modes bimodal, right? The main thing that I want you to remember is, well, one, bimodal distributions are really rare. But if you find a bimodal distribution, okay, I'll highlight this, it's possible, okay, possible or even likely that two groups have been combined into one data set when they should probably be analyzed separately. Okay, so if you see a bimodal distribution, maybe have a look at some of your categorical variables, right? Maybe you're able to split these two groups up, right? For example, maybe, well, the easiest thing would be maybe it's a group of males and a group of females, and we're talking about, I don't know, how much they eat in a day or something weird like that, right? And so we should probably analyze those separately and maybe compare those two groups, right? And so that's the main thing about bimodal distributions. Okay, good. So the reason that we need to be able to talk about the shape is because the shape dictates how we should calculate the center and the spread. Okay, and so I'll bring this lump in here so we can talk about it. Wait, hey. So depending on if we have a normal or non-normal distribution, right, we're going to talk about these numerical measures of center and spread. So, right, we had those rough approximations, and then now we're going to develop calculations for how do we deal with these things. So if we have a normal distribution, then the measure of center that we should use is the mean. Okay, the mean is the average. Right, we've already talked about the mean. And a lot of these things we haven't talked about yet, but I'm introducing them as we go. Okay, so we use the mean as the center for a normal distribution, and we'll talk about why that is, right? And rather why we can't use the mean for a non-normal distribution. Okay, and so if you have a non-normal distribution, the measure of center that you should use is the median. Now, we'll talk about the median later, but the median is just the data point that splits your data in half if you've sorted it from smallest to largest, right? And we'll go through and we'll do some examples. Yeah. The spread, typically we talk about the standard deviation. Sometimes we'll talk about the variance. Now you'll see the standard deviation is just the square root, the positive square root of the variance. Okay, so our measure of spread is going to be the standard deviation if we have a normal distribution. Okay. I'll highlight these here. Whereas our spread, if we have a non-normal distribution, right, then we should be using the interquartile range, which we'll talk about as well. Okay? But it's really just the difference between the middle two quartiles, right? You split your data in quarters instead of in half. Okay? But we'll get there. So the median and the interquartile range, even though we've only prescribed them for the non-normal distribution, we can calculate them for a normal distribution, okay? But if we have a normal distribution, then using the mean and the standard deviation opens up a lot more calculations that we can do. So a lot more analyses that we can use. So, so here, right, we can use the median and the interquartile range for any distribution, right? Even normal distributions. But they're the only reasonable measures of center and spread for a non-normal distribution, right? If you have a normal distribution, cha-ching, and it opens up a lot of doors for us, and then we can use the mean and the standard deviation to do our calculations. Okay, so that's why, right, going back to when you're looking at the shape, that's why we always should argue that we have a normal distribution, maybe with the exception of some outliers. Right? Oh yeah. So how I like to do this, instead of showing you how to do everything and then go through and actually have an example, instead what I do is I'm just going to talk about all the things that I could ask you to do, okay? And then we'll work through and actually do these with one example, okay? And so I might ask you to find the mean, which means we have to know how to do it, but then I'll show you how, so I'll tell you how to do it, and then we'll do an example. Same thing with finding the standard deviation, okay? Should probably find the variance first, but we'll switch those up. Let's not do a stem and leaf plot because they're really stupid and we're not living without computers anymore. Clearly, we're meeting online. Our phones can make histograms now. So stem and leaf plots are basically like a poor man's histogram. So I'll show you what they look like, but it's not something that I want you to do. We're going to be using software to do all these visualizations. So I'll give you the histogram to describe the distribution, right? So remember, when we're describing the distribution, that's one of the few things that we've already done. We have to talk about the shape, the center, and the spread. Okay. Then we're going to find the median, right? So I'm going to show you how to find the median, and then I'll show you how to find the interquartile range. Okay. The IQR is the interquartile range. Then it says give the 5-number summary. So of course I have to tell you what the 5-number summary is. And then we're going to answer if there are any outliers. Now there are specific rules that we're going to follow to determine if we have any outliers. And then finally, I want to show you how to make a box plot. Now, that's not because I want you to make a box plot. We're going to look at the anatomy of a box plot, but of course we're going to use R to create these box plots. Okay. So I'll do all these with one example. So referring to the same data set throughout, and that data set is this one. And kind of classic, I remember I've used these notes before, obviously, and there was a typo somewhere, and I feel like I fixed it because I couldn't find it. But there might be a typo, but probably not. And the typo was that 2 lines were missing here, but I think we're good. All right, so just kind of introducing the data set, right? So the success of companies expanding to developing regions of the world depends in part on the prosperity of the countries in those regions. So here are the World Bank data on the growth in domestic product, so the GDP % per year for the period 2000 to 2004 in countries in Asia, not including Japan. So here it looks like they're listed alphabetically, right? Bangladesh, China, Hong Kong, India, Indonesia, Korea, South Korea, Malaysia, Pakistan, Philippines, Singapore, Thailand, Vietnam. So we have this numerical variable growth, right? Or the GDP, if you want to call it that instead, right? And so country would be kind of the observation, or we could call it a categorical variable if you wanted to, right? But the variable that we're interested in is the GDP, and that's a numerical variable. Right? Makes sense because that's the section that we're in. We're analyzing numerical variables. So here we go. Okay. Notice that we've got all these numbers here, and there are a lot of things that we already know how to do. For example, if I asked you to find the average GDP, what would you do? You would add them up and divide by 12, I think it is, but let me just confirm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so from there, we can see that N is 12. N, remember, is our sample size. Okay. So we have a sample size of 12. Okay, so you denote it by, and I guess got a little sloppy there. All right. So if we start working through those questions, right? The first question was find the mean. Now what I've done is I've also included some R code. So the first thing I want to do is just show you how to enter this data, the easiest way to enter this data into R. And you don't have to be doing it now, but just so you can see what's going on here. So I say R, but of course I'm working through RStudio, okay? And I'll show you guys maybe once we finish this chapter, then I'll go through and I'll show you guys just how to do these things in R, right? But I've got these here so you can play around with them. And so what I've done is I've called this variable GDP, right? So you can give it one name, no spaces. It can't handle spaces. It has to be just one thing, but it can be multiple letters long, right? And so here I've called it GDP, or you could just call it G if you want. Okay. And so here, this is what I'm calling, this is the variable name. Okay. So later when I type GDP, then R knows that, oh, that's actually the list of all these numbers, right? It's an array, and this is like the easiest way to enter data, okay? Well, it's not the easiest, but it's the simplest, let's say. The easiest way is just to bring it in from some existing source and then just use it. That's easy. But here, if you have to enter data, then what you do is you use a little C. C is for concatenate, I think. I'll have to brush up on my R terminology, but I think concatenate which means just connect, right? Right, so join these all up. And so this creates an array. An array is just one column of data, right? So concatenate creates an array, which is just one column. Oops. Of data. Why did I put quotes around column? Well, because when I say column, I'm thinking back to an Excel spreadsheet, right? It would be a column in my Excel spreadsheet, but here it's just a list of numbers, okay? So you have to be careful, right? When you enter your data points, each data point has to be separated by a comma. But besides that, all I've done here is I've just typed out 5.2, 9.4, 3.2. I just did them in order, right? One thing that I do to make sure that I've got the right numbers, at least, just to have an idea, is I would just confirm once you've typed them all out, right? Then just confirm, just count how many you have here. It should be 12, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, looks good. Because you're relying on how you entered this data, right? You could have a data entry error. So it's always worthwhile to check to make sure that you copied them in correctly, right? Usually we're going to end up using data that already is in R, so it's built in. But this is one of those rare cases where it's easier to just plug it in, right? Have it there. Okay. Okay. So far, not bad. Oh, we didn't talk about this arrow. So what you do, this is a less than sign followed by a dash, and it just means a sign. Okay. We can use equals as well. And I'm old and grumpy, so I usually just use equals. The reason we shouldn't use equals is because there are some very, very rare cases where it wouldn't work. It breaks it. Okay, and so we shouldn't use equal signs, but I get lazy. An equal sign is only one stroke, and a less than dash is 2 strokes. That adds up. But if you're being proper, and I want you to be proper, you should use the less than dash. But we should use less than dash. There's no space there, but I just want to show you that it's 2 things. Okay. If doing things properly. But confession time, sometimes I slip up and I'll use an equal sign. Try not to, but I can't shake it, right? I've never had a problem with it, and so I feel confident. You know, if you really just want to use an equal sign, that's okay, but you will be ridiculed on the internet if you post something with an equal sign. Just beware. All the cool kids use this one here. Okay, and that's what we should be using. Okay. I don't know if you guys have read things on things like Stack Exchange. So a lot of the time, if you're working in R or any sort of programming language, most of what you're doing is just Googling how to do stuff. And that's the game, right? That's the game that we're playing. And so how do I do this? How do I do this? I guarantee you that someone has already tried to do what you're doing, right? And so it's just trying to find, you know, an answer that works, right? And things become outdated and things like that. So you have to keep digging. But I'd say the majority of my job when I was working as an analyst was just Googling how to get it to do what I wanted it to do. So we have to be a little bit creative, right? Oh, I want to try to do this, right? I want to try to create this thing. So we have to be creative, right? And then it's just a matter of figuring out how to make it do the thing that you thought that you wanted to do, right? And so it's really just a game of finding how to do stuff, right? And so that's what you'll find. And that's the frustrating part too, right? Because you can't just read it. Well, I mean, you could sit down and read a textbook, but a lot of programming, so we are programming in R, a lot of programming is just going to be trial and error, right? Just kind of getting used to it. Seeing errors is also really valuable, right? So seeing it say, hey, I don't know what you understood or what you're saying, that's valuable as well, because then you learn from that. Okay, so more about just kind of the frustrations of R later, but for now, this is how you would enter just this little bit of code. Okay, so now that we have that entered in R, notice how the font here is slightly different, right? So when you see that font, that's our code that you can run. Okay. And maybe what I'll do at the start of tomorrow is I'll show you how to enter it, because I don't have it set up today, but tomorrow I'll show you in the beginning how to enter it and run some of these commands. And also right here, I've got more R code, right? The mean of GDP, just off the top of your head, what do you think that's going to do? So when you read this, mean bracket GDP end bracket, I read it as mean of GDP, so typical function notation, right? And so the mean of GDP, it just calculates it, is 5.10833. So let's go through and talk about it. How do we calculate it by hand? Of course, that's not something that you have to do, but it is something we need to understand sort of what it's doing, right? But in terms of actually applying it, we don't have to actually calculate it by hand anymore. That's insane. Although I know some profs still feel that it's really valuable to be able to read these complicated formulas and kind of dissect them and understand them. For me, nah, right? It's good to be able to see them and not be scared, but then just, we don't actually have to do these crazy calculations anymore. That's insane. All right. So what we're going to do is usually we use x, a lowercase x, to denote the variable. So it's just a shorthand for the variable. So in this case, I'm saying let x be the growth and domestic product, so the GDP. X bar, and shoot, I feel like we've talked about x bar, right? The sample mean, right? So x bar in this case is the sample mean of the GDP. Yeah. Now, in terms of the formula, so on the formula sheet that I'll post, but you're going to be making your own formulas because it's open book. So our tests are open book. And so I'll post a formula sheet so that you have something to work off of. And this is one of the things that would be on there. But x bar, which is the sample mean of x, okay, is the sum of the x's. So here, I'm just going to bring this down so we can talk about it, because part of it is just being able to read this and not be scared, right? So here, this says the sample mean of x, right? Where x is just a placeholder for any variable, okay? A numerical variable. And here, the sum, and this can get kind of complicated. Sometimes there's an x subscript I to denote each individual data point, right? x1, x2, x3, x4, x5. I have omitted that because it makes it look a little bit cleaner. But if you see that, just ignore the subscript. It's just saying sum up all the x's. So sigma, capital sigma, is a capital sigma, right? So it's a Greek letter, and it's the sum. Right, or we call it summation notation. Fun to say, some fun to do. Summation notation. Okay, and so the sum of x is just saying add up all the x's. Right? Which is what you would do, right? If I asked you to find the average of those numbers, right, you would add them all up and then you would divide by however many there are, right? But however many there are is n, our sample size, right? So here, just as a note, x subscript 1 is the first data point. X subscript 2 is the second data point. And I guess in X. So in general, we call it X, but then X1, X2, X3, all the way up to X subscript N which is the final data point because that's how many data points you have. So in general, we say that we have the nth data point in X, right? So that's just good to have a good handle on, okay, it's really not that bad, right? In terms of our numbers that we're dealing with, right? This is X1, X2, X3, X4, X5, blah, 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 all the way up to X12, okay? The order that we assign these is arbitrary, right? We're just listing them, so they could be switched about, doesn't matter. So if we want to find the sum of the x's, right, you just add them up. And so then this becomes one thing. Oh, sorry, it's just catching up. The sum of x is 61.3. Okay, so if you add those all up, you get 61.3. So now this is a placeholder for the sum of those x's. Okay, and so here, let's see here, got more. Okay. So if we look at our formula that we're working with, right, even though it's got this kind of summation notation, which I don't know how familiar you are with summation notation, maybe a little bit from Calc 1, but I don't know. And so it looks bad, right? But we can replace the sum of the x's with 61.3, and then we're off, right? So then we can divide by 12, and x bar, the sample mean of x, is roughly 5.11, right? Because I'm rounding. Notice that I guess it says we, but notice that I've rounded the answer to 2 decimal places. That's arbitrary. Sometimes I'll tell you how many decimal places to go to, but definitely at least 2 is safe, right? 2 is kind of the minimum number of decimal places typically. But one thing that I want you to remember is that you should keep all the decimals throughout your calculations, right? So you should try to keep all your decimals. And so that's where software becomes really important, right? Because it's able to remember all these decimal places and it can just use the exact values, right? And so you should only round in the final step. And then round to at least 2 decimal places. So I'm going to highlight this because it's something that I want you to remember. If you're doing calculations by hand and you need to use a result in later calculations, for example, if you had to use the mean of x, so x bar, in a later calculation, which we will, you're allowed to use the rounded value. Right? So if you've already rounded it, then you're allowed to just use the rounded value, right? But I'll kind of show you what's important and when you're allowed to round later. But this is our first thing that we're calculating. So it's good to lay the groundwork here. So how we find the mean in R is we just say, okay, now give me the mean of GDP rather. Right? And so here, function notation, f of x, for example, the mean of GDP. Oh, we're done. Here, I'm just, sorry guys, but last note then, I'm done, I promise. Time flies when you're having fun, I guess. You guys are like, not really. Right, and so the true mean would be 5.108333, right? And so any output is kind of followed by pound sign. And that's it. All done. I'll see you guys tomorrow. If you have any questions, let me know, but otherwise, see you tomorrow. Let's see.